Hello class. Today what we are going to look at is perpendicular and angle bisectors. So perpendicular bisectors and angle bisectors. Now we have already talked about both of these in previous lessons. We know that a perpendicular bisector is something that bisects a segment and it is perpendicular to the segment. So it is perpendicular to the segment and it bisects the segment. We call it a perpendicular bisector. Now, so first then we have here the perpendicular bisector theorem says that in a plane, if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what that means is we have this line right here, line CP. That is the perpendicular bisector of segment AB. So any point on line CP is going to be equidistant from point A and point B, which means that segment CA is going to be the same length as segment CB. Real quickly, equidistant. That probably does need to be defined. You may not have seen that term before. What equidistant means is equal distant. Distance. Equal distance. It means they're the same distance. Means these segments are going to be the same length, so the segments are congruent. All right. So what that means is CA is the same length as CB. And it doesn't matter where C is, because C could be here, C could be there, C could be way down here. It doesn't matter as long as it is on that line that is the perpendicular bisector of segment AB. Then CA is the same length as CB. Okay? And the converse is also true. All right? What this says is that if some point D is the same distance from A and B, if it's equidistant from A and B, then it must be on that perpendicular bisector. All right. So since D is equally distant from point B and point A, then D must lie on line CP. Must be on that perpendicular bisector somewhere. All right. That's what this says. All right. So let's take a look at this. Let's open this up, see what we got. Okay, so in exercises 1 through 3, we want to find the indicated measure and explain our reasonings. We have to explain. Everybody's favorite thing to do. So let's see. In number 1, we need to find the length of segment AB. So how far is it from point A to point B, looking at our picture here? Well, we have a triangle, 2 triangles. We could do lots of things with this, but we want to use the stuff that we've been talking about, perpendicular bisectors, right? So segment AD, we notice it is perpendicular to segment BC, right? And since BD is the same length as BC, that means line AD is the perpendicular bisector of segment BC. And as we saw before, perpendicular bisector, if a point is on the perpendicular bisector, then it is equidistant from both endpoints. What that means is that point A is the same distance from point B as it is from point C. So since A is 9 units from point C, it is also 9 units from point B. So AB equals 9. And I need a different pen. Throw that one away. So AB equals 9 because this is the perpendicular bisector theorem. Okay, so let's take a look at EG. EG, from E to G. Well, let's see here. We do have a perpendicular line. It would be nice if HG was the same as EH, right? Perpendicular bisector, but it doesn't show that it's a perpendicular bisector. It just shows it's perpendicular, not a perpendicular bisector. However, we do know that point F, FG is 7 units, FE is 7 units, and so, let me put this down. That means FG is the same length as FE, so that means point F is on the perpendicular bisector of segment at EG. All right. So F is on this perpendicular line. There's only one perpendicular line through a point from a line. So FH must be the perpendicular bisector. So that means that FH is perpendicular bisector of EG. How do I know that FH is the perpendicular bisector of EG? This is the converse of the perpendicular bisector theorem. So, if this is a perpendicular bisector, then one, not only is it perpendicular, it is also the bisector, which means HG is the same length as EH. So HG must be 3. So how long is EG? Well, EG would be EH plus HG, and so that is 3 plus 3, which equals 6. So far, not too bad. Remember, if it's a perpendicular bisector, the point is equidistant from both sides, basically turns it into an isosceles triangle. And over here, if it's equidistant from both sides, meaning it's basically an isosceles triangle, then it is on the perpendicular bisector. So these two will be the same length. Okay? So let's take a look at number 3. Slightly more complicated, but just because we have variables. So it's not a big deal. We've been using variables for years. No big deal. All right, we want the length of SU. So S to U, which we know is 2x plus 2. And we have that's 3x, which, what are we going to do with it? We have to set this equal to something, or add it up and equal to something. We're going to do something with it. What are we going to do? Well, we have this is 10 and that is 10. So what that means, point R is on the perpendicular bisector because it is the same distance from point S as it is from point T. So if this is the perpendicular bisector, which I know because it's the same thing here, converse of the perpendicular bisector theorem. All right, so I'm going to go ahead and put that down. That means that SU is congruent to UT. So I can set those two equal to each other. Solve for x. 2 equals x. That's not my answer. It doesn't ask for x. It asks for SU. So always pay attention. All right? A lot of people find x and stop, but it wants you to find SU, which means you have to take the x, plug it back into SU. So SU, the length of SU, equals 2 times 3 plus 2. So the length of SU equals 2 times 3 is 6, plus 2 is 8. All right? So not too bad. Not too bad. Now, we're actually going to get to some that is a bit complicated, and I'm sorry for that. If I knew a way to make it easier, I would, but I don't. If you find a way to make it easier, let me know, because I like easy. Here we go. We need to find the equation of the perpendicular bisector of segment AB. So we are looking for the equation of a line that, number 1, is perpendicular to segment AB, so it's going to be going this way somehow. And number 2, it's going to go through the midpoint of AB, wherever that is. So that means we've got to find two things. First, we have to find where's the midpoint. Second, we have to find the slope of the line, right? Because you have to have a slope and you have to have a point. Got to have a point of both of those. So step 1, we're going to find the slope, because we'll find the midpoint, whatever. All right, so step 1. Step 1 is the midpoint. So how do you find the midpoint? You use the midpoint formula. And we remember that. That is x1 plus x2 divided by 2. And then we have y1 plus y2 divided by 2. So let's see here. From this one, we have a and b. So x1 is the x value here, so that's 0. Plus x2, which is for b, that would be 2 divided by 2. And then y1. So y1 is negative 2 plus y2, which is 2 divided by 2. So 0 plus 2 divided by 2, well, that would be 2 divided by 2, which is 1. And then negative 2 plus 2 is 0 divided by 2 is 0. So that is my midpoint. All right, so we found our midpoint. Let's go ahead and mark that over here. I'm going to do that in a different color. Put that right there, and I'm going to call it point M. point M for midpoint. Okay, so now we have a point. Every line has to have two things: a point to start with, and then it has to have the slope. So now let's find the slope. So step 2, slope. Okay, so everybody should remember slope. Slope's pretty easy to find. So there's lots of ways to do it. Okay, rise over run, changing y over changing x, y2 minus y1 over x2 minus x1. Lots of things to do. Now what we're going to do is we're going to find the slope of AB. And I'm going to do this. I like changing y over changing x, changing y over changing x. So I look at here and I say, well, my y's, I'm going from -2 up to +2, so I want up 4. Then I look at my x's, changing x as well. I'm going from 0 to 2, so that goes up 2. And 4 over 2 is 2. Now, my problem with this is that this is the slope of line AB. I don't want the slope of line AB. I want the slope of a line perpendicular to line AB. So since I'm going perpendicular, I need a perpendicular slope. And if you will recall, perpendicular slope is opposite reciprocals, or negative reciprocal, however you want to do it. It is the negative multiplicative inverse, whatever. Here's what you can take this, multiply by it equal -1. Or I can just take this, let's see, that would be 2 over 1, write it as a fraction, flip it over, and it is 1 over 2. This is positive, so I want negative. There we go, there's my slope. Perpendicular slope is going to be -1/2. All right. That's step 2. Step 2 is easy. Step 3, last thing we're going to do here. Step 3, write the equation. Okay, 2 ways you could do this. You could just start in slope-intercept form, plug in what you know, try and figure out what B is, and then rewrite your equation. Personally, I like point-slope form. Personal choice, if you like slope-intercept form, then by all means, use slope-intercept form and go straight from there. I'm going to use point-slope form, which, if you'll remember, is y minus y1 equals slope times x minus x1. And now I'm going to plug in what I know. Y is just y. Minus y1 is the y value of my midpoint, the point that I have, so 0, equals m, my slope, which is right here, this -1/2, times x is x, minus x1, which is the x value of this point, so 1. And now I'm just going to simplify this, get y by itself, so it's still going to end up in slope-intercept form, which is good. So y minus 0, well, minus 0 doesn't do anything, so that's just y. All right. Now over here, I want to get rid of these parentheses, so I'm going to take this -1/2 and I'm going to distribute it in. So -1/2 times x is -1/2x. -1/2 times -1, well, a negative times a negative is a positive, and 1/2 times 1 is 1/2. And so this is my equation. That's why I like point slope form. I find it very, very easy. Now, that's not going to be good enough for me. I do want to draw this because that would just be a lot better. I have a graph. Let's use the graph, right? So let's see, I have a slope of -1/2. I'm going to start from point M right here. Slope is -1/2, so I'm going to go down 1 and right 2. So down 1, right 2, put a dot right there. That doesn't give me a whole lot. I like to have more than 1 dot, more than just 2. It only takes 2, but I like to have more than that. So now I'm going to go backwards. So instead of going down 1 and right 2, I'm going to go up 1 and left 2. Puts a dot right there. Do that again. Up 1 and left 2. Puts a dot right there. Grab a straight edge. Never freehand anything. Always use a straight edge. And that gets us this line here. And there we go. That is our perpendicular bisector. As you see, It has opposite slopes. I actually do have a protractor here, so you can see that is that's a right angle, 90 degrees there. And it is a bisector. I could measure this, I suppose, just to prove it. There you go. We've got about, what is that, 1.3 and 1.3 there. So there you go. You generally won't actually do that with the protractor and stuff, but just so you can see it. Important thing, if a point is equidistant from the endpoints of a segment, it is on the perpendicular bisector. And if it's on the perpendicular bisector, it's equidistant from the endpoints of the segment. This is the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. Hopefully you found that useful, and I'll see you in the next video.